To close this section, we will consider one more operation, the resolution or decomposition of a vector into two vectors. You can think of this as a kind of inverse addition. If we were dealing with a real number, let's say 5, we could ask how many ways we could break down or decompose the number into two smaller constituents. If we were restricted to integers, possible combinations would include 1 plus 4, 2 plus 3, or 6 plus minus 1. If all real numbers were permitted, a continuum of combinations would be possible. In any case, there would be an infinite number of possibilities. In the case of vectors, possible combinations are complicated by the fact that vectors have direction in addition to magnitude. There is again a continuum of possibilities, but we make a further distinction between orthogonal decomposition, that is, decomposition into vectors A and B that are perpendicular to one another, and non-orthogonal composition. Our movie shows a continuous set of non-orthogonal decompositions first, followed by a continuous orthogonal set. Going forward, we will most often be interested in resolving vectors into orthogonal or mutually perpendicular directions. The reason is that equilibrium in each mutually orthogonal direction can be expressed independently of the other directions. This will ultimately permit us to turn a 2D problem into two 1D problems and a 3D problem into three 1D problems. Especially in 3 dimensions, it is far easier to think about three one-dimensional statements than a single 3-dimensional statement. If orthogonal resolution or decomposition is so useful, you may wonder why we would even be interested in non-orthogonal decomposition. Perhaps we have a force applied to the joint of a structural lattice whose members are not configured in mutually perpendicular directions, and we want to resolve the force into components along the directions aligned with the lattice. In any event, we want the flexibility to resolve vectors into either orthogonal or non-orthogonal directions. In summary, there are an infinite number of ways to resolve vectors into components, whether they are resolved into orthogonal or non-orthogonal coordinate systems. Once the component directions are specified, the resolved components A and B are guaranteed to be unique. Orthogonal decomposition is straightforward. If we know the magnitude of f and the angle, we'll call it theta, that it makes with one of the axes, the magnitudes of its component vectors follow directly from the definition of sines and cosines. In this case, sine of theta is defined as the ratio of the opposite side of the hypotenuse, so that's b over f, and therefore we can write b as f sine theta. Cosine theta is defined as the ratio of the adjacent over the hypotenuse, and that immediately gives us that a is equal to f cosine theta. Non-orthogonal decomposition may be a bit more work, but the laws of sines and cosines can be used to find the magnitudes of the component vectors. If we know the angle between the non-orthogonal axes, I'll call it phi, and we know the angle made by f with one of the axes, again I'll call this theta, then we can find all the angles in one of these triangles. The angle psi would be equal to phi minus theta, and given the parallelogram sketched here, this would also be psi. So this remaining angle here would be 180 minus theta minus psi. Having one magnitude, f, and all the angles allows us to use law of sines to find the magnitudes of the remaining two sides, which gives us the component magnitudes we're seeking. As a final example, we have a problem involving a surfboarder tacking into wind such that the force perpendicular to the sail is 40 pounds. We want to resolve this force into two components, one parallel to the surfboard's direction of travel and one perpendicular to its direction of travel. In this case, we'll begin by sketching one orthogonal coordinate system that is parallel and perpendicular to the direction of the surfboard's travel. It's also the case that the sail makes an angle of 25 degrees with the perpendicular direction, and the force in question is perpendicular to the sail. What we have here is two mutually orthogonal coordinate systems. Knowing the angle that the sail makes with the parallel direction of the surfboard's travel being 25 degrees, we can fill in the remaining angles, and all of these angles will also be 25 degrees. Our force is along this direction and equal to 40 pounds. We want to find the parallel and perpendicular components of that force, and we can do so very simply using the properties of right triangles. So here F parallel is equal to F sine of 25 degrees, and that is equal to 40 pounds times sine 25 degrees is 16.9 pounds. And F perpendicular is F cosine 25 degrees, which is equal to 36.3 pounds.